All right, today we're going to do some new stuff, position. So we're going to look, starting, we're going to look at force position graphs. So this would be a graph not of a force applied over a time, but a force applied over some distance. So if you were pushing a box and you were pushing it with a constant force over some amount of distance, what does that do to the box? Or any force in that case. So let's suppose that we had a box of mass m and we're pushing that box. And let's suppose that we had a surface that had friction on it. Typical surface. So I'll say I'm going to push this desk. Push this desk at a constant speed until it runs into another desk.
That would have been awful.
Ended your baseball career? Me pushing this desk? So we're going to push this box, and on this box we're going to push it at a constant speed. Now if I'm pushing it at a constant speed, what is happening to the total energy of that box? It's remaining constant. What type or types of energy does this box have when it's being pushed along a rough surface like that? It has kinetic type of energy. Kinetic or potential. Those are really the only two major categories of energy. How could it have potential? Right, it's on the surface. So it doesn't have any potential energy, or doesn't have any gravitational potential energy, but it has kinetic energy because it's being pushed at a constant speed. And as my position changes, as my delta x changes, what's happening to that energy? No, it's got friction. And the energy is going down while I'm moving at a constant speed? No. It's the same. Yeah, I'm moving at a constant. How can I be moving at a constant speed? If I'm pushing on a box, how can I be moving at a constant speed? The friction equals the amount of the force that's being done. So let's first identify those forces with a free body diagram. What does the free body diagram of that box look like? Normal force and mg. Friction to the left. Force person, force push to the right. Which one of those forces is doing work on the box? None of them are doing work on the box? FP and friction are both doing work on the box. What about the normal force? And mg? No, because they're perpendicular to the direction of motion, or perpendicular to the delta x. So they don't do work on the box, but force of the push and friction are both in that plane that the object is moving, so they are both doing work. So if they're both doing work, why doesn't the energy change? Because they're doing the same amount of work, except one is doing positive work and one's doing negative work. Let's look at the graphs of these two forces. So let's do this. Do them both on the same graph, and we'll do red for the force of the push. So if I'm moving at a constant speed, let's say that I started with this much force. What happens to that force over my position? If I move at a constant speed, what happens to that force as I go? It's also got to be constant, so it's constant like that. Well, let's suppose I apply that force over a distance x1. Let's call it x1 or just some value x. How much work did I do? We'll call that the force of the push. How much work did I do in pushing that box a distance x1? Work done by the push is the force of the push times the change in position. So the work I did is Fp times x1. And is that positive work or is that negative work? That's positive work. Why do you know it's positive? It's in the same direction as the position change. Now, would you also agree that F is the height of this rectangle and x1 is the base of that rectangle? And so therefore, F times x1 is the area of that rectangle. And so we could say that the work done is equal to the area of that rectangle. Okay.
So is this kind of like the thing under the heart?
Yeah. It's just like the other areas that we talked about. What are the areas of graphs that we talked about?
So, something.
Area of a something in a position.
The area of under the water. Area under the curve of velocity.
Yes. Area under the curve of a velocity time graph is a change in position. Is a new area. Area under a force position graph is the work done on that object. Area under a force versus position graph is the work. Oh, area under a velocity time graph is position change. That was from a month ago. Well, that's not the only force that's doing work on this thing, because if it were the only force doing work on this thing, what would happen to the energy? It would be increasing because work was done, and work would cause that change in energy. And since we've already concluded that the energy is not changing, we've got to identify some other work that's happening as well. So what else is doing work in this? Friction. And we'll draw that on the same graph, except we'll draw green. So where is the force of friction going to start?
Where it starts moving.
Is it going to start at 0? Is it going to start higher than f of p? It's going to start at fp. And
Go down this. Goes to kinetic friction.
well, it's moving already. So the thing's already moving. So what's going to happen to that frictional force over time, or over position? It's also going to stay the same. It also is going to be constant. Kinetic friction is going to be constant over that time interval and therefore the position interval. So if I was going to calculate the work done by friction, it would also be the area under that curve. And what's the area under the curve equal to here? Fpx1. It's the exact same area that we had before. So the work done by the friction is equal to the work done by the push. What's the difference between the work done by friction and the work done by the push? They're in different directions, and therefore the work done by friction is going to be negative. And so when we find the total amount of work done, that's the work done by the push plus the work done by friction. Work done by the push is equal to the work done by friction, except it's opposite. These two things did equal amounts of work, and therefore the total amount of work, if I add these two together, is 0. So we call work tot equals those two things. And if the total work is 0, what happened to the energy? The change was also 0. So the work total equals the change in energy, which is 0. See how all these things are hopefully coming together? Hopefully. So what if I give you a graph? We'll put some numbers on this. Force position, we'll say that's 5 meters. That's 10 newtons. Let's just kind of step through this. We'll call this net force. So the total amount of force that acts on the object starts from 0 here and increases as the position changes for a total of 5 meters. See if we can describe what is going to happen to this object. Will it remain at 5 meters per second? No. How do you know it's not going to remain at 5 meters per second? How do you know it's accelerating? There is a force acting on it, and a force causes an acceleration, and an acceleration changes its velocity. So we know for sure that this thing is not going to be at the same velocity later on. Now, can we use F equals ma to calculate the acceleration of the object? No, we can't. Why can't we do that here?
No, because it's not a constant force.
It's not a constant force. The force is changing as the distance progresses on. So I could calculate the instantaneous acceleration there. Say that's 5 newtons. Well, I could say 5 newtons equals 8 kilograms times a. That would be the acceleration at this point right there. But then, as it moved just a little bit further, that force would be different, and therefore the acceleration would be different. So I can't simply use F equals ma in this case. So how do I find out this new velocity? I can't use F equals ma to calculate acceleration. Work. What is the work represented by in this graph? The area under the curve. So if this graph has area, which it does, and that area is equal to the work, what's work equal to? The change in energy. So if I can figure out how much the energy changed, can I figure out how much energy it started with? Yes, I can. So if I know how much energy it started with, and I know how much energy it changed by, I can figure out how much energy it had in the end. Okay. Can you figure out?
At 5 meters.
Sure. So I know how much energy it starts with. What type of energy does it have? Kinetic. So it has kinetic energy. I do work on the object, so I'm changing the energy of that object. So if I know how much it started with, and I know how much it changed by, I can tell you how much it has in the end. All right, so that's the progression here. Anytime you see work, you can think change in energy. How much did I have? How much do I have now? If you want to kind of mathematically show it, we can say that work is change in energy. So work is the final minus the initial. In this case, we know the initial, and we can get the work. So the final amount of energy equals the initial plus however much work was done, right? So that's the end amount, how much I started with and how much changed. Finish, start, change. New is equal to old plus change. Yeah. Oh, is that from calculus?
Yeah, like the integrals.
Well, you're looking at one.
The area under the curve.
Yeah. So, for those of you who like the calculus,
No, we don't like it.
Literally stop now.
None of us like it.
if you integrate
No.
a force with respect to position function, that equals
Yeah.
work. So if you have a force function as a force as a function of position,
So that.
and you integrate it, that will give you the amount of change of energy of the object. It's the area under the curve. Don't worry about it.
I can't right now.
For those of you who understood that, you should take the C APC next year. Be a great class for you.
I'll graduate this year. Let's go.
Wait, what?
All right, so yeah, it's the natural course of the AP classes. You're encouraged to do it, actually. All right, so let's go through this. Let's find out how much energy. Now, why do we care about how much energy it ended with? How's that going to help us?
Because that can help us determine acceleration.
No, it's not going to help us determine acceleration, but it will help us figure out what the final velocity is. So what was the initial energy of this thing? Let's start from the beginning. How much energy did this thing start with?
100 joules.
The kinetic energy is 1/2 mv squared. Mass of the object times the velocity that it started with squared. So 5 squared
Point bar.
On top of the whole.
times 4,
100
100 watts,
joules.
joules. So this thing started with 100 joules of energy. How much did that 100 joules of energy change by? Okay, question.
Why do you have the second squared in it?
Oh, sorry, my bad. I got a little anxious to put that square on there.
Okay, so now what did you say after you wrote that down?
It has 100 joules of energy to start with.
Okay, great.
So let's figure out how much that energy changed by. How do we figure out how much the energy changed by? The area under the curve. Now this is a triangle, so remember your old geometry. 1/2 base times height. So the work in this case is going to be 1/2 base times height. Or we could say 1/2 base times height. Height is force, base is x. But wait, yeah, well, wait, yeah. Because we know that work equals force times x. Why does it not equal force times x in this case?
Because force is increasing.
It's changing. This is only good for constant forces. So, bear with me on this. What is the average force over this interval?
That.
1/2 F.
Wait.
5 newtons.
Okay.
All right, we're going to do these things side by side just to show you how we get.
Okay, wait. First question.
Okay, question.
Try f x like x times f, just to make it look like the other function.
Yes. Yeah, height times base I wrote, just to make it look like the other one, yes. This equation is only good under constant force, but if the force is changing constantly, then we can use the average force in that equation too. We maybe should come back to this. Let's finish up our problem here first, and then we'll come back and we'll do that next to it. So the work is equal to 1/2. What's the height of that thing? 10 newtons. And the base of it is 5 meters. So how much work was done? 25 joules.
How important it is.
Very important. So it started with 100. It changed by 25. So what was the final amount of kinetic energy it had? 125 joules, assuming that the force was applied in the same direction. If the force was applied in the opposite direction, what would happen to the energy? It would decrease. So we'd have to be more specific in the problem. Yes. How would you use that to find the velocity? Right. That 125 joules is now equal to 1/2 mv squared. 125 joules is 1/2 8 kilograms times whatever the new velocity is. And it'll be some, I chose weird numbers, so what's it? 8 is 31, square root of 31 is what, 5.5? 5.2, something like that? What's the answer? Right. You can think of that as v final. That's it. We just found the final velocity. So basically, here's the situation. We had an object that was moving at 5 meters per second. We came behind it and we gave it a little push, but we didn't give it a constant push. Maybe we caught it and then started, and then we started running afterwards. So we're giving it a push that's constantly increasing its value. By applying that push, we have accelerated it. Not constantly, but we have accelerated it. And we gave it additional velocity. So as a result of that push, the box went from a 5 meters per second to 5.6 meters per second. It increased its velocity. Okay. This is an example of what we call the work energy theorem. All that says is it's a general expression that says if I do work on the object, I change the object's energy by the amount of work I did. It's never not true. It's a theory. I mean, we've been kind of doing it all along, but this is an example of it in practice. This is general energy, though. It can be any type of energy. The first problem we did in this chapter, we raised something up, so we changed its potential energy. In this case, we're changing its kinetic energy. We could change both at the same time. We could change its spring energy. We could change its rotational energy. This is any type of energy change. Now, let's take a look at this other option for doing this.
We don't have this.
But we have a constantly changing force. So that means we can find an average force over that interval. what's the average force? So if I, over this interval, what's the average force? It's 10 plus 0, 2, right? That's an average. So that's 5 newtons times what distance? 5 meters. So how much work did I do? Sorry, that's 5. Right, that's the idea. That's right. This is the average force of that interval. Right. This is exactly the same as if I applied this average force of 5 newtons over the entire interval, because the area of this rectangle is equal to the area of that triangle. I haven't drawn it to scale very well, but it is.
But then, like, why would you use that other equation?
Why would you use this?
No, the other.
Oh, this?
Why? Yeah. Why?
Let's say we had a weird shape. We could calculate the average of that weird shape. We may not be able to find the area of that weird shape. I'd have to find a nice weird shape.
Like a sinusoid curve?
Sure. Okay. So just kind of a real quick. You'll be able to see the symmetry of this, but yeah, that's okay. Fine. I could find the average of this force, which is 0. It's harder to take the integral of this function, but I could find the average of that function much more simply. I'll have to write an example that works. It's kind of hard to come up with one on the fly for that.